Jai Hind everyone, myself Sandeep Yadav, Assistant Professor CSC Department. In the series of lectures being organized on complex topics of DBMS, I am here before you to deliver a lecture on functional dependencies. So the topic is functional dependency. So outline of my lecture is functional dependency, definition and types of functional dependency, inference rules, closure of set of FDs, and closure of attribute. First of all, we will study what is functional dependency. Now, consider a relation R. Consider a relation R having n number of attributes from A1 to AN. These are the attributes up to AN. Now, we have the relation student having the following attribute: roll number is there, name is there, marks is there, and grade is there. So, now let X and Y be the attributes, these attributes of relation R. If the value of component X of a tuple determines the value of Y, then we say that X is functionally dependent on Y. That is, this is denoted by X is functionally dependent on Y. This part is known as determinant and this part is known as dependent. X part is known as the determinant and Y part is known as dependent. For example, consider the case of marks and grade in a class. So, marks determines the grade. Every student is aware that his or her marks determine the grade. So, marks determine the grade. So, in any relation, some of the attributes determine other attributes. The determining attributes are known as determinant and the attribute whose value is being determined by other attribute is known as dependent. Now, diagrammatic representation of FDs. Now, X, there is an attribute X that is determined Y. So, this is represented in this way, X determine Y. Suppose two attribute X1 and X2 determines Y, then we will say X1 comma X2 determine Y. In this way, we will show X1, X2, both of these together combined determines Y. Next is a single attribute X is determining two attributes Y1 and Y2. So, this will be represented in this way, X determine Y1 and X determine Y2. Now, consider an example of relation account having the attributes account number, balance and branch. Account number can determine both balance and branch. So, there is an FD from account number to balance and branch. How to represent this? Account number is determining balance and account number is determining branch. So, we can say that FDs are the attributes which shows relationship with other attribute of the relation. They are the prime determinant in any of the relation base. So, this is diagrammatic representation. Account is determining balance as well as account is determining branch. Now, FDs are of following types: full functional dependency. In a relation, the attribute B is fully functionally dependent on A if B is functionally dependent on A but not on any proper subset of A. In other relation, consider the following example: roll number is determining semester, roll number, semester and department is determining SPI. We need all these three attributes to determine SPI. SPI is student progress index. So, all of these three are being used to determining this attribute SPI. if we remove department semester from here, then it will not be possible for roll number and department name to determine SPI. We need all these three attributes. If we remove any attributes, then we are not going to determine the SPI. So it need all the attributes. Now next is partial functional dependency. In any relation, if attribute B is partially functionally dependent on A, if B is functionally dependent on A as well as any proper subset of A. For example, suppose A and B is determining C and A is determining D. That is, A and B are determining C, and a part of this, a subset of this attribute, A is determining D. Then that is an example of partial functional dependency. If there is some attribute that can be removed from A and still the dependency hold, then that is known as partial dependency. For example, there is enrollment number is there, department name is there. Both of these attributes determine SPI. Now enrollment number is sufficient enough to determining SPI. So this is an example of partial functional dependency. Third is transitive functional dependency. Transitive functional dependency means if A determines B and B determines C, then we can say that A determines C. That is transitive dependency. Consider the following example of a subject and faculty table. There are three entries: subject, faculty, age. Subject is DS, faculty is SA, age is 35. Second is DBMS, faculty is Patel and age is 32. Third is DF, faculty is SA and age is 35. Now subject is determining the faculty, subject is determining faculty and faculty is determining age. Then we can say that subject determine age. This is transitive FD. So as per the rule of transitive dependency, subject should determine age. This FD should be holding. Next, we have trivial and non-trivial FDs. In trivial FD, X determine Y is trivial if Y is a subset of X. For example, roll number, department name and semester determining roll number. Clearly, this roll number is the subset of these attributes. Second, so this roll number is subset of roll number, comma department, comma semester. Second type of FD is non-trivial FD. X is determine Y is non-trivial if Y is not a subset of X. In previous example, this was a subset. Here X is not a subset of, the keyword is not a subset of X. Roll number, comma department name, comma semester determine the student name. But we see the student name is, this student name is not subset of, this student name is not subset of roll number, department name and semester. This is different attribute and these are different attribute. This is not part of here. So Y is not a subset of X. This example can be considered an example of non-trivial functional dependencies. Next, we will be studying some of the rules, inference rule related to functional dependencies. There we will be studying inference rule. With the help of these rules, we can try new FDs, we can find out the candidate key, we can determine the closures. So basically these rules are the foundations for functional dependencies. Now first rule is reflexivity rule. if B is a subset of A, then we can say that A determines B. Second is augmentation rule. If A determines B and C is a set of attribute, then we can say that A C determines B C. This rule is known as augmentation rule. Now third rule is transitivity rule. If A determines B and B determines C, then we can say that A determines C. This is transitivity rule. These three rules are known as, first three rules are known as Armstrong axioms or rat axioms. These rules do not have any proof. These are basically axioms, means they are supposed to be true. We don't need any verification to prove them. So these first three rules are known as Armstrong axioms and rat axioms. These are complete and sound because they allow us to generate another FDs. Next rule is pseudo transitivity rule. If A determines B and BD determines C, then A D determines C. This is pseudo transitivity rule, a very important rule which is used in computing the closures. Next is decomposition rule and union rule. Union rule is if A determines B and A determines C, then union rule states that A determines BC. We simply take union of this and this, that is A determines BC. Now decomposition rule is just reverse of union rule. A determines BC means A determines B and A determines C. Now these last three rules, rule number 4, this rule and this rule, these need proof. For example, A determines B and A determines C. We can say that A determines C, but we need to prove it. Let us see how we can prove it. A determines B, then we can write A C determines BC. Now A determines C, right? Then we can say that A dot A determines AC, that is A determines AC. Now this is second and this is first. From first and second, using transitivity rule, we can say that A determines BC. In the similar fashion, from first and second, we can say A determines BC. In the similar fashion, we can also prove decomposition rule and pseudo transitivity rules. These are very essential rules. These rules will be needed in computing various closures as well as for the better designing of the relational database. Next is closure of set of FDs. Now given a set of functional dependency, there are certain functional dependencies that are logically implied by F. Means what new FDs we can derive from the existing FDs. We can use closure to compute that set of FDs. So basically closure of set of FDs is used to derive new FDs using inference rules. For example, A determines B and B determines C. So using inference rule, we can say that A determines C. So the set of functional dependencies that is logically implied by B is known as F plus, that is this is F plus. This is the closure of set of FDs. So we will be applying the inference rules to find out new set of FDs from the given FDs, so that we can make a better database design. Now let us see one example. Suppose we are given a relation A R having the attribute A, B, C, G, H, I and set of FDs F. Set of FDs are A determines B, A determines C, CG determine H, CG determine I, and B determine H. So what new set of FDs we are going to derive? Now first new set of FD that we have derived is A determine B and B determine H. This means A determines H, that is using rule number 3rd, that is transitive rule. So using transitive rule we have determined that A determines H. What new FDs we can find out? Now another, see here, CG determine H and CG determine I. Now CG determine HI. Why? Using which rule? We are using the union rule, that CG determine I. That is using the union rule we are saying that CG determine I. Now let us apply some more inference rules to get a new set of FDs. Now A determines C and CG determine I. Now this means AG determine I using pseudo transitive rule. Now we will be applying pseudo transitive rule here. A determines C and CG determine I, then AG determine I. Using pseudo transitive rule we can say that AG determine I. This is another set of new FD. This is also a new FD that we have computed with the help of existing attribute, like we have done in the previous slide. Now functional dependency, A determines C and then we can apply the augmentation rule. AG determine G. We have augmented both sides by G. Then we will be getting AG determine CG. This is also a new set of FDs that is not present here. There is no FD here. AG determines, there is no FD here which says AG determine CG. This we have derived using augmentation rule. Now AG determines CG and CG determine I, then applying the transitive rule we can say that AG determine I. We are applying transitive rule on these and we will be getting a new FD, AG determine I. Now this is the set of FDs that we have derived here. In this example, A determine H, CG determine HI and AG determine I. So this is the closure of set of FDs that we have determined for this particular example. Likewise, now let us consider one more example. There is a relation R having the attribute A, B, C, D, E, F, and the set of FDs are given. A determines B and B determines and A determines C, CD determine E and CD determine F and B determine E. Now we have to find the closure of F, means we have to derive some new FDs. So let us see. First, A determine B and A determine C, then using union rule we can say that A determine BC. Second, CD determine E and CD determine F, then we can say that CD determine EF. Which rule? Again we are using union rule. Now next is A determine B and B determine E, then we can say that A determine E, that is using transitive rule. Next, A determine C and CD determine A determine C and CD determine E, then A D will determine E, that is using pseudo transitive rule. Now A determines C and CD determine F, then again AD will determine F. Again we are using the pseudo transitivity rule to find out this FD. Now let us sum up what are the new set of FDs that we have got is A determine 1, A determine BC, second CD determine EF, third A determine E, fourth AD determine E, and fifth AD determine F. Now we have got 5 new FDs. These new FDs will help us to make more clear regarding the dependencies, new dependencies that were not present. They will bring out new patterns as how the relations are being dependent on each other, as how one attribute is being dependent on each other, what relation exists, what dependency exists. So these are revealing certain new dependencies existing in our database that we were not aware earlier, but using the closure we can find out this set of FDs. Now next, one more example, compute the closure of set of FDs for relation R, where relation R is having the following set of attribute. R is equal to A, B, C, D, E. These are the FDs and these are the attributes. Basically these are the attributes of the relation. These are the attributes of this relation. So the relation is having 5 attributes and set of FDs AB determines C, D determine AC, and D determine E. Now we have to find out the F plus, that is the what new FDs we can derive is, first is A D determines AC. How we can say that D determine A and D determine C, using which rule? Using decomposition rule. So here we have in the second FD we have applied decomposition rule. Using decomposition rule we will be getting 2 new FDs, D determine A and D determine C. Second, D determines A, C and D determine E. Now applying the union rule, that is rule number 4, D determine ACE. So what are the new set of FDs? Finally we have got is D determine A, D determine C and DC determine D determine AC. So how many new FDs we are getting? We are getting 3 FDs. So total we have got 3 new FDs. In this way we can compute the closure of set of attributes. Now next is we have to find the closure of attribute set. Now closure of attribute set, given a set of attribute alpha, the closure of alpha under F is the set of attribute that the set of attribute that are functionally dependent by alpha under F. It is denoted by alpha plus, that is alpha plus. Whatsoever attribute is there, that will be denoted by alpha plus. It can be computed for a single attribute, it can be computed for a set of attributes. Now why we are computing closure of attribute set? The question is, the reason is basically we want to find out the candidate key or the super key in our given relation. So in order to find out the super key or the candidate key in our relation, we have to determine which attribute encompasses all the other attributes. If the closure of that particular attribute determines all other attributes, we can say that that is candidate key. So closure of a attribute set is basically used to determine the set of candidate keys in a given relation, because if you are able to find out the candidate keys of a relation, only then we will be able to apply the process of normalization, whereby we will decomposing our relation into new and simpler relation so that design become easy, and various problem like anomalies, insertion, deletion, or the problem of data redundancy become minimized. We cannot remove redundancy. Basically, we can only try to minimize the redundancies. Now, let us see what are the steps that are followed in computing alpha plus. There is an algorithm. Now, algorithm to compute alpha plus, initially result equal to alpha. Second step, while change to alpha, do for each fd, beta determines gamma in f, do begin if beta is a subset of result. Initially result equal to alpha. Now, if beta is a subset of result, then the new result will be equal to result union gamma, else result equal to result. Now, let us use this algorithm to find out the closure of attribute. Consider the relation R equal to A, B, C, G, H, I. For this relation, a set of FDs can be given. For example, F relation that set of FDs are A determines B, A determines C, G determine H, CG determine I, and B determine H. Now, we have to find out the closure of AG plus. Now, we will be using the algorithm. Number one step, initially result equal to AG. Initially result equal to AG. This is the first step. Now, second step, this first FD A determine B. Now, this A determine B. A, the part that is on the LHS, this one is a subset of AG. This A is a subset of AG. Then result equal to ABG, that is AG union B, that is ABG. Next step, next FD is A determines C. Now, this A again is a subset of A, B, G. Now, the new result will be A, B, C, G. Now, next FD is CG determine H. Now, this CG is a subset of this. Yes, CG is a subset of this. Yes, this is the subset. CG is a subset of the result. CG is a subset of result. Then the new result will be there. Now, the result is A, B, C, G union H. That is, the new result is A, B, C, G, H. The new result will be A, B, C, G, H. Now, next, CG determine I. Now, this CG determines I. This CG is again a subset of the result that we have computed, that is A, B, C, G, H. Now, result equal to A, B, C, G, H, I. Now, next, B determine H. Now, B is a subset of A, B, C, G, H, I. Now, result equal to A, B, C, G, H, I. Now, no longer we are being able to add any other attributes. See, this is already here present. So, our result set consists of all the 6 attributes A, B, C, G, H, I. Our result set consists of all the attributes A, B, C, G, H, I. Now, we can say that AG is the candidate key for this relation. Now, we can also try to find out the A plus. Now, this A determines B, that is A plus is AB. Now, next, this A is also subset of this, that is this become A, B, C, and this is also A, B, C, H. Now the closure of A comes as A, B, C, H. No longer we can add more attribute to this relation. So A plus A is not the candidate key. Only the attribute, that attribute will be the candidate key whose closure consists of all the attributes of that relation. So A is not a candidate key. Similarly, we can try for other attributes also, and the attribute whose closure computes all other attributes, that will be the candidate key. Now, given a set of FDs for relation schema R, relation schema R is A, B, C, D, E. Now A determines B, C, D determines E, B determines D, and E determines A. Now we have to find out the closure of A, closure for CD, closure for B, closure for BC, closure for E. Now let us see how to find out. Very easy. For A determines BC, so the closure of A is A, B, C. Now B determines D, now A, B, C, D. Then A determine E, so the closure will be A, B, C, D, E. Now again we have to determine the closure of CD. Now CD determines C, CD determines C. Now the closure is CDE. Now E determines, CD determines E. Now closure is CDE. Next CDE, we will be able to find out that closure of CD plus is A, B, C, D, E. Similarly, the closure of B is B and D, because no other FD is derived from this. The closure of BC is, similarly we find out that the closure of BC is A, B, C, D, E, and the closure of E is also A, B, C, D, E. Now clearly we are seeing there are 4 candidate key. A plus is there, CD is there, BC is there, and E is there. So there are 4 candidate key. One of them may be selected as primary key, and rest of them can be used as alternate key. Okay, thank you everyone. This is all from my